Hey guys, so in this video I'm going to review how to find electric fields for various continuous charge distributions, and we're going to go take it one step further and start finding the potential difference for these various shapes. So I'm just going to try and let all this video play and just kind of talk over it, so bear with me. We're going to start off with a ring. It's one of the easier shapes to do, so this is for electric field. So remember that the trick for finding a ring is that the radius little r stays constant at all points around the ring, so the distance between each little tiny charge dq and the point in question, point P, stays the same, and it ends up that all of those little electric fields that are generated, only the x component is going to matter. So yeah, the calculus is kind of nasty. That cosine theta pops up in order for us to get only that x component. Crunch everything together, simplify everything, and you just get the integral of dq, which just turns into big Q, the total amount of charge. Okay, so that was a review. Okay, we can also find the voltage from a ring of charge, so bear with me. This is voltage, yes. So we know that voltage is equal to the negative integral of E dot dr, so there's me just plugging in the electric field equation that we derived before. We have to do some U substitution for that x squared plus r squared term down in the denominator. You go through that, you crunch everything together, it turns out pretty nice. We end up getting kq over the square root of x squared plus r squared. If you imagine as x goes bigger and bigger and bigger, as it gets closer and closer to infinity, the more and more similar this result is going to be just to like the voltage from a point charge, just kq over r. So that makes sense. We're good with that. We've got one more calculus derivation before we can start doing Gauss's law. So this disk was pretty gnarly. Like the hoop, only the x components of the electric field are going to sum together because all of your y components are going to cancel out. For this one, we're taking a surface charge density and just kind of rearranging it. You get that cool little trick where you take the derivative of area and you get circumference. So there's that. You can see I'm going through here. I tried to color code stuff as much as possible. There's more U substitution. Lots of stuff cancels out, thankfully. Gross, you get a negative sign. You evaluate this guy from 0 to big R, the radius of the disk, and you get that really ugly thing. Now, this next one hurts my heart. This one took me a while, but I did it for y'all. Here's the voltage of the uniformly charged disk. So we start out by saying that voltage is equal to the negative integral of E dot dr. I copied and pasted my electric field from the previous slide. I split apart my integral because I got scared. I did some U substitution, and yeah, it's that. I doubt that you will ever actually have to do this on the AP test, but hey, it's there if you want it, or if you stumbled upon this video from somewhere else, hey, that's how you do it. Alright, so that was the nasty calculus stuff. We can kind of tone it down now and use Gauss. Because Gauss's law, again, works for highly symmetrical systems, such as infinite lines of uniform charge. So remember that Gauss's law says that the flux is the surface area integral of E dot dA, which is also equal to the charge enclosed divided by that constant epsilon. That surface area integral of dA is just the area of the cylinder wall. So crunching stuff together, you get that the electric field is has a 1 over r relationship to the distance from that line. The voltage one gets a little weird. Because it's infinite, you can't really say that your voltage is 0 at infinity, so we're going to say that the voltage is 0 at some arbitrary point big R. That's what that lower bound on my integral represents. And so, since this one you're integrating with respect to 1 over r, you're going to end up getting a natural log. If you remember your log rules, you should end up with 2k lambda natural log of big R over little r as your potential difference. Okay, so now we're going to talk about spherical conductors. So with a conductor, the convenient thing about that is, well, if it's charged, the charges are going to try and spread out as far as possible from each other. So they're all going to be gathered along the surface, which makes the inside really easy to evaluate for both electric field and for potential difference. When you try to do Gauss's law, well, if there's no charge enclosed, there's no charge on the inside, then the electric field is zero. On the outside, you should hopefully be familiar with the electric field due to a point charge, kq over r squared. It makes sense. A sphere looks an awful lot like a point. So that works out well, and you can see that graph in the top right corner. Now, the only tricky thing about voltage, and this will trip you up if you're not careful, when you try to do v is equal to the negative integral of E dot dr, right, and the electric field on the inside is zero, it doesn't mean that the potential difference is zero. In fact, if you think about, well, so voltage is very closely related to potential energy. It's the amount of potential energy per coulomb of charge that it would require to bring some positive point charge from infinity to the point in question. It would take a lot of energy to drag a point from infinity to the center of this spherical conductor. So it's not zero, right? It is going to be constant, however, and so more on that in a moment. Okay, figuring out the outside, you should just end up with the standard potential difference equation for a point, because, like I said, a sphere is very similar to a point, and we generally say that our initial, or our reference point voltage is zero, located at r is equal to infinity. Your voltage graphs are never going to be discontinuous. They are definitely not differentiable all the time, but they will be continuous. So if at big R, at the surface of the conductor, we have a potential difference of kq over big R, then that must be what's constant throughout the inside of that conductor. So you can see the graph shows it better than I could ever explain it. But that's what that's going to look like. Okay, add that to your list of graphs to memorize. Okay, last but certainly not least, I struggled with this a lot. First, I want to mention that the outside of your insulating sphere is going to be just like the outside of the conductor, so I'm not even going to bother with doing the electric field or doing the potential differences for the outside. We're really just focused on the inside, because that's where things are really different and really painful, to be honest. So for the inside, you can see your electric field is going to be linearly dependent on R. Okay, this should be a very familiar graph to you. It looks like the gravitational field inside a solid planet. Okay, so this first method I have for deriving voltage here in this middle column is doing an indefinite integral and having quote-unquote V naught kind of as my constant of integration. Like, it's the plus C that people tend to forget when they're doing indefinite integrals. So again, that boundary condition at big R, right, at the surface of your insulator, has to be continuous. So you can see in that 1, 2, 3, fourth line of red, I set up my function for V at big R must be equal to KQ over big R, and I plugged in and I solved. So I solved for quote-unquote V naught, okay, and I rearranged to get that lovely thing, KQ over 2R times the quantity 3 minus little r squared over big R squared, close parentheses. Okay, there's an alternate derivation which I almost like more. This one, since potential difference is a scalar quantity, you can just kind of add up each individual integral. So I've set up V is equal to the negative integral from infinity to little r, right, little r being the point in question, of E dot dr. Well, we already know what the integral of E dot dr is from infinity to big R, right? That's just going to be the potential difference for a point. The tricky part, again, is that inside part. And so it's kind of weird. We're going from the outside in. So, because we know what the voltage should be at big R, and so we're going to go inwards towards little r. So that's what we have in that bright blue there. And so we just kind of go through. It gets a little gnarly. You can do some cool stuff with factoring, and turns out, sure enough, I did get the same answer as I did before, so I did it. The graph for this looks really unique. The first part of the graph between 0 and big R, so like within that sphere, is quadratic. It's an upside down parabola. It's a frowny face. Okay, your peak value is obviously going to be at the center of that sphere. It would take like the most energy to bring a point and stick it right in the middle of that sphere. So even though at that point, like if you're truly at r is equal to 0, your electric field is 0, so your force is 0. It is a point of equilibrium, but it is highly unstable. Right? Remember, we talked a little bit about equilibrium and potential energy, like the various types of potential energy. The smallest nudge would move that test charge and give it tons and tons of energy. The electric field would be doing tons of work on it if it were nudged out of r is equal to 0. So that's kind of interesting there. Outside of the insulator, it's just going to go as the inverse of r. Whew. And that's all of the derivations that you could possibly need. It's probably more than you really need. We're not going to spend too much time on it. They're here for your reference if you want them.